Okay, so let's get started again. So we're going to talk first about radiative losses, also called Bremsstrahlung radiation. So radiative energy losses are due to the emission of electromagnetic radiation during scattering with the absorber atomic nuclei. And this is called braking radiation or Bremsstrahlung. And it's much more significant for electrons and positrons than for any other particles. So you can see how to think about this in the lower part of the slide. So for our ionization, we were thinking of our charged particle coming in, exchanging our photon with an atomic electron. Now for this radiative loss, we're talking about an electron coming in, emitting a photon, and then scattering from the atomic nucleus, and then scattering off and continuing. So in a kind of more schematic sense, you can see here the electron, here it is, it emits its photon and then scatters from the atomic nuclei. So one might wonder why this is significant at high incident particle energies and indeed for low mass particles like the electrons. While deriving the rate of energy loss by Bremsstrahlung is rather involved, and I have here only a kind of approximate relationship. So you can see here that the dE by dx, the loss, energy loss per unit length from radiative losses is proportional to the energy of the incident particle. So you can see this E term in here. So the higher energy electrons impart more energy to the emitted photon. And it's also proportional to 1 over m, so 1 over m squared in fact. So the radiative energy losses for muons are some 40,000 times less than for electrons at precisely the same energy. So in fact, muon Bremsstrahlung only really becomes significant at a momenta of above about 500 GeV, so really very energetic. So if we think about electron Bremsstrahlung with this expression up here, then one can rewrite that in a form where one has an energy over a term that we call x0, where the x0 term is given by this much more complicated expression on the right. And this is in fact how we define the radiation length x0, which typically has units grams per centimetre to the minus 2. One can divide by density to get x0 in then centimetres. So given we have this equation then for dE by dx related to the E and x0, one can see that the solution to that is going to be that the energy is equal to some initial energy, and then there's an exponential fall off with the decay constant in here being x0. And from that one can understand that the radiation length is the mean distance over which a high energy electron loses all but 1 over E of its energy by Bremsstrahlung. And so all but about 63% of its energy. Okay, so that brings us to our next topic, which is Cherenkov radiation. This is the light that's emitted by a medium, that's excited by a charged particle going through it. And in fact, the particle needs to be moving faster than light can move within a given medium. And Cherenkov radiation is actually what's responsible for the eerie radioactive glow that you may have seen associated with, for example, nuclear reactors. So this shows you the kind of light one can see from a nuclear reactor. This is the Cherenkov effect, giving light out in the water that's used to cool the reactor core. And the amount of radiation depends on the velocity of the particle involved. So what's going on here? Well, as the charged particle goes through, it polarizes the medium. So if this particle were negative, it would draw positive charges towards it and repel negative charges in the atoms of the material, and therefore one would get a kind of polarization effect. If you're traveling relatively slowly with beta or V over C less than 1 over the refractive index, then the emission that results from this acceleration of these charges is incoherent. So one gets radiation, but one doesn't get a coherent wavefront. But when you go fast enough, when you have a beta factor that's larger than 1 over n, then as you move through, the different wavefronts that you create from the acceleration of these charges, they line up, and one then gets a coherent wavefront. One can derive just from geometry the angle of the radiation comes out at. So this side is CT over N, this is VT, and so the cosine of the angle of the radiation must be CT over N VT, so is 1 over N times the beta factor. So, as I've already said, coherent radiation is emitted when the charged particle exceeds the speed of light in the given medium. The photons are emitted at an angle cos theta equal 1 over N times beta, and therefore there's a threshold for emission of Cherenkov radiation, which is that the beta factor must be 1 over N. And then one can have different kinds of Cherenkov detectors. One can have so-called threshold Cherenkov detectors, which only determine the presence of the light. However, one can also have detectors which measure the angle as well. These are the so-called ring imaging Cherenkov detectors, or rich detectors. And one final possibility is so-called Dirk detectors, which detect internally reflected Cherenkov light. Okay, so one final topic then is that of transition radiation. This is the radiation that's emitted when a particle moves between media with different refractive indices N1 and N2. The intensity of the radiation in this case is proportional to the gamma factor, but the emission angle is actually inversely proportional to the gamma factor. The radiation that's emitted is mostly X-rays, and the emission probability is rather low. So if one's to use this transition radiation effect, one needs many, many layers and extremely high gamma factor. So gamma's typically of around 1,000. So for electrons, one can get this transition radiation for momenta above about 500 MeV, whereas for charged pions, one needs something like 150 GeV in order to get a sizable effect. Alright, so that brings me to the last topic I wanted to cover, which is the energy loss of electrons, positrons, photons. So let's go on and just do a quick survey of those types of energy loss. So one can separate photon interactions into a kind of low, medium and high energy regimes. In the low energy regime, the predominant effect is the so-called photoelectric effect, where the photon comes in, interacts with an electron, and then that electron in itself interacts via a photon with a nucleus. At medium energies, one has Thomson or Rayleigh scattering, which is elastic or coherent scattering against free electrons, and also Compton scattering at intermediate energies, which is inelastic or incoherent scattering against electrons. And then finally, at very high energies, one gets pair production or annihilation processes. So let's start by thinking about the photoelectric effect. In this case, the photon energy is completely absorbed and it's transferred to an atomic electron, which is ejected. The energy of the electron is related to the energy of the photon and the binding energy, or the so-called work function of the material. And that's shown by this expression here. And the cross-section for this kind of interaction is given by z to the fifth divided by the energy of the photon. So you can see on this log scale for the photoelectric cross-section versus the photon energy that there's this very steep fall off given by this z to the fifth. Okay, so this gives us the idea for photomultipliers. These are extremely light sensitive vacuum tubes that have a photocathode deposited on the inside of some window. This is some material with a very low work function. So when an incoming photon strikes this, they emit electrons, and those electrons, by some amplification, we can then turn into a current which we can read out. Next up is the Compton effect. In this case, the amount of energy re-exchange really varies as a function of angle. So the energy of the outgoing photon E primed is related to the incident energy E, as shown in this expression, where one has this 1 minus cos theta expression in the denominator. So the maximum energy is transferred here when theta approaches 180 degrees. However, it's impossible for the photon to transfer any more energy beyond this point. So there's then a sharp cutoff at this maximum energy, giving rise to the name Compton edge. So if you look at the number of counts as a function of energy, one can see the Compton effect resulting in some energy loss right up until the effect falls off at this so-called Compton edge. Okay, then pair production. If you're going to have pair production, you must have the energy to produce 2 electrons. So you must get twice MEC squared, which is about 1 MeV. In this case, the cross-section is quasi-independent of the energy, and there's this rather involved expression for the cross-section you see here. And in fact, the mean free path for pair production can be related to the radiation length x0, and this modification factor, if you do the full calculation, of about 9/7. All right, so there's a final quiz on this section. Again, go to mentimeter.com, and here's the code for this final quiz to check your understanding of what I've said. So 90, 92, 51, 2. Have a go at that, and thanks very much for your attention for this first lecture.